I've been working on numerical calculations in quantum mechanics, and this is something I've already done. This is a finite difference calculation for a Gaussian wave function starting in an infinite square well. And it's a kind of a complicated calculation. I did it already, but basically you break this into finite space points, finite distance points, and then you can kind of use the differential equations to model the thing out. It's kind of cool. It's really cool. I like it a lot. But there's another way to solve this problem, and that's what I'm going to do today. So I'm going to show you how to make the same thing, but with using a superposition of states in the finite square well. Infinite square well. There's a lot of Python here. There's some math. It might take a while. I'm probably going to make a mistake, but I'm going to do it. And it's going to be cool. Or not. Okay, so we want to reproduce this, but another way. And this is one of the things I like about quantum mechanics, right? We have these complicated, complex even, differential equations, and we want to solve them. And there's multiple tools that we can do to solve that. You know, I could find the stationary states. I did that. I could find... I could use the shooting method to find the finite states. And see here, I wanted to waste my time. You can see here what's happening in this finite difference method. It's starting to get a little wonky because the calculation errors pile up. But that's still a pretty good solution. Okay. And I have a video about how to make that. So let's do this another way. I'm going to switch over here to another Python program, and I will give you the code. But let's jump over to the paper and talk about what we're going to do. Okay, so this is the infinite square well. So it has starts at x equals 0 and it goes to x equals a. The sides have an infinite potential, so the particle cannot go in there at all. We have the Schrodinger equation. I'm not going over this in super detail. I have a video on this. Also, with the analytical solution to the infinite square well, the stationary state. The key here is that this wave function psi depends on both x and time. It turns out that we can split it into a space part, lowercase psi, and a time part, which turns out to be this exponential e to the negative I e t over h bar, and e is the energy eigenvalues for different levels. And we have these energy eigenvalues because in order to match the boundary conditions at x equals 0 and x equals a, we have this function. And so there are various values of n that will work, and these are our eigenstates. That's what we have so far. Okay. So it turns out that if I have this as my wave function, then I get a stationary state. It stays there. Right? It doesn't change. But what if I have something like this? What if I want to put the Gaussian in here? What if I want to put this function in there? Well, it's not going to stay. We just saw it didn't stay, right? We can actually solve this function and look at its evolution by saying it's a superposition of multiple of these. I've already shown that if you have two different functions right here in an infinite square well, if you have energy psi 1 plus psi 2 with different values, then you get an oscillation in here, but it still works. And it turns out that you can have up an infinite number of these. And in fact, I can represent psi of x and t, this is the key here, as a sum, an infinite sum from n equals 1 to infinity of some coefficient cn times the wave function psi n of x e to the minus I, that's the I, e n t over h bar. So if I do that, and I know these solutions, and I know the e's, and that's the I, then I can just say it's a whole bunch of these things, right? It's a whole bunch of these, and I can model it out. Now, how do I find these coefficients? It's a lot like finding the coefficients, in the fact this actually is, of a Fourier series. I can find, C, because I have a sign there, Cn is going to be the integral from negative infinity to infinity of psi n of x star, complex conjugate, psi of x 0 dx. So if I know the initial wave function right here, and I know the solutions, I can find C1 is going to be the integral over all space, which is just going to be 0 to a, because there's no function over here, there's no function over there, of psi 1 of x. I don't have to put the complex conjugate because that's not a complex solution, of psi x0 dx. And I can find that. And then I can find C2. And then I can find C3. And then I can find C4. And you get the idea. And then at the end, I'll say psi of x and t will be C1 psi 1 e to the negative I e1t over h bar plus C2 psi 2 e to the minus e e2t over h bar plus C3 and so forth. And these are all things I know. So I can just plot it, right? I don't have to do a whole bunch of calculations. And I don't have to worry about the errors getting bad and stuff like that. The only thing I have to worry about is, am I going to go to infinity or not? But it turns out that, as we will see, these coefficients get smaller and smaller and smaller numerically as they get into higher orders, and so I can just ignore them. So I'm not going to go to infinity. I'm going to go to like 8, but whatever. Okay, so we have a bunch of things to get done here. I'm going to need to calculate the energy levels, E. Okay, so let me write this down. I need to calculate and I do have something else I need to work on. But let me come back to that. I want to just plot. I want to plot my initial wave function. So let's say psi of x and 0. And you'll notice here the nice thing, if I put in t is 0, then this term is 1, so I don't have to worry about that. Psi of x and 0, what did I use before? I want to use the same thing. It's going to be equal to 1. I used 1. I think I'll normalize this. Let's just call this a. X minus a e to the negative x minus a over 2 squared. That's my initial wave function. I just want to go ahead and plot that, normalize it, find a, and then we'll come back and talk about finding some other things like the energy, the wave functions. I am going to need a real and imaginary part, and I'll show you that why. But let's just get this first. Let's just break this into parts. So I'm going to plot this. Let's do that in Python, and then we'll come back. So when you're working in Python, I'm switching it right here. When you're working in Python, you want to think about chunks. You're going to make mistakes. And if you try to do everything at once, then you don't know where the problem is. But if you do it in chunks, you can make sure this chunk works, and then the next chunk works, and so forth. I am using WebVPython. That's what I like to use. It doesn't have a lot of the built-in functions for like matrices and stuff like that. So you have to do a lot of this on your own. It doesn't have the NumPy arrays, which is a super awesome tool. But that's fine because it makes us think about what's going on. And this is the goal here is not to make the perfect calculation. It's to practice calculations so that we can understand what's going on. And that's what we're doing. Okay, and I'm learning too. I'm not a huge expert in quantum mechanics. If you're watching my videos, I'm not that. This is not my area. But I'm teaching the class, so that's why I'm doing this. Okay, so here we go. I have some stuff entered in here, and let's make this bigger. That's good. I like big because people like to see what you're writing. Right? Is that even big enough? I think that's big enough. So I made a graph. I didn't put any titles on it. Let's put a title. Y title equals stuff, right? Because I want to plot both the psi and psi star psi, so I'm just going to call it stuff. It's not going to be anything. And then the x title is x, and that's fine. And then I'm going to plot this function f1. I'm going to call it a g-curve. Here's my space, my initial x, so I don't know why that's 0. The length of my well, a. My time step, h bar is 1, m is 1, t is 0. I got dt. Let's see, what else do I need? Let's just go ahead and make this function. Now, the other thing that we're going to do is we're still going to make things in a list. So I'm going to add my x values to a list. I'm going to add my functions to a list. That way, I can go back and reference those lists because I'm going to have to do things like integrate and things like that. So let's make some lists. I'm going to make my list called x. It's a list, an empty list I'm going to add to it. I think this needs to be a little bit bigger. Okay, that's better. X is an empty list. And then I'm going to have my initial wave function, which I'm going to call just psi 0 is an empty list. And I'm going to have my mover variable, I'm going to call this xt, and that's what I'm going to move all the way to a to add to the list. So let's do that. While xt is less than a, I want to first add to my x list, x equals x plus xt. So now I'm building up a list of x values. Now I need to build up my psi value too. So let's do that. And this is where I'm going to use my calculation. And you could write a function for this, so I'm not going to. Psi 0 equals psi 0 plus, what do I want to calculate? Oh, I want to have a equals 1. And we can change that. A times, now I'm just writing this equation right here. I'm writing that equation. X, now I'm xt, that's my temporary variable I'm moving along, times xt minus a times the exponent of negative xt minus a over 2 squared. So I'm adding that to my list. Now I need to move my x value up. Xt equals xt plus dx, or this loop will go on forever. And let's just see if this works before I even plot it. I'm going to print the length of x, right? See if that is what I think it should be. Run. Okay, 61. That seems right. So we can save it now. Superposition solution. 1D infinite square well. I don't know what I'm talking about. Okay, I'll probably never find this again. I'll have to find it through my video because I'll put the link in the video, and that's how it's easier to search. Okay, so now we can graph it. I'm going to plot psi. Should I plot psi? I'm going to plot the probability density. Now let's just plot psi, just to make sure it's working. Okay, so I want to go through my list and plot. So let's do it this way. For I in range length of x, right? This will make the value of I go from 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 60 actually. And then I can use that I as a reference for x and psi. And I can just plot. f1.plot xi psi 0 I. And that should be it. That's it. Okay. So that's my initial Gaussian wave function. Yes, it would have a positive probability. But actually, let's do the following. I want to normalize this, and then we'll go to the paper. So because that's not normalized, let's plot psi star psi by just squaring that. It's just data. I can just square those numbers, and I get that. Okay, obviously it's not normalized because this goes up to 80. So let's normalize it and calculate A. To do that, I'm going to make AT equals, let's call it P total. P total equals 0, because to normalize, I'm saying the probability over the whole thing has to be equal to 1, right? Which is psi star psi dx. I have to integrate psi star psi dx over the whole thing. And I'm going to call that my total probability, P total. And each time I look at a point, I need to calculate psi star psi times dx. And then add it to the total. So I need to start with the total. So let's do that up here, and we'll use that total to calculate A. For I in range length of x minus 1. Right? Because if I'm integrating, let me draw a picture. I have time, right? You have time. You're still here. You probably have time. So if I'm integrating, because we're going to integrate again. If I'm integrating and I have finite data points, like that. Oh, that was bad choice right there. So if I'm integrating, and let's say this is psi star psi, and this is x, I have my dx's are my distance between here, right? And I want to actually add up the length of the area of that box, that one's 0, plus the area of that box, plus the area of that box, plus that one, plus that one, plus that one. But that's 1, 2, 3, 4, 5, 6, but I have 1, 2, 3, 4, 5, 6, 7 data points. So I don't want to go to that last data point, even though if you did, it would be fine because it's 0. But I want to be legit. Okay, so I want to do one less. I want to do my sum over one less of my data points. And that's why it's length of x minus 1. Oh, I'm down here. Colon. And now I'm just going to calculate the sum over that box and add it to p total. So p total equals p total plus psi star size, which is going to be psi squared, psi 0x, no, I squared times dx. So psi star psi is the vertical, or psi squared, and dx is the horizontal, and that's the area of the box, and I add it to the total. Now I can take a equal to a divided by the square root of p total. Now, actually, what I really need to do is go through and fix all my values of psi, which I need to do before I integrate, and this is important. So I don't just need to, I can recalculate a if I want to, recalculate all my psi's, or I can just fix it. Let's just do this. For I in range, I can do it right here. I'm going through this loop right here. I can change my values of psi 0. So psi 0i is going to be equal to, I changed the value of a, so I can just recalculate everything. Oh no, I can't, because I don't have my xt's. Let's just do this. Psi 0i is equal to psi 0i divided by the square root of p total. All right, then it should be normalized. Let's just plot it, and we should be able to visually inspect that it's normalized. And square root, right, because I'm normalizing psi squared. So each of them have to have a square root of p total divided by it. And I messed up. P, aha. I see what my error is. I did lowercase p total somewhere. P right there, which I didn't even use. Okay, so it goes up to less than 1. You can imagine that if I integrate this whole thing, I do get 1. I think that's obvious. Okay, so I have my function normalized. What do I need to do now? Now let's look at my solutions to the infinite square well, because I'm going to need e, I'm going to need psi, and I'm going to need a real and an imaginary part. Okay, and why do I need a real and imaginary part? So let's jump back to the paper and figure that out. Yes, this is going to be a long video, but that might be a good thing, right? Okay, so the first thing is I'm looking at this. Psi n of x equals square root of 2 over a sine n pi x over a. That's I need that as I'm going to do that so often, I'm just going to make that as a function. I'm going to make that as a function. Now I need to deal with the energies, right? The energy comes up because it comes up in time. I have this e to the negative I e n t over h bar. And there's two problems here. What's e? I'm going to define that as a function. E n is equal to n squared pi squared h bar squared over 2 m a squared. And again, if you don't know where that comes from, that's fine. I have another video on that. I'll post it down below. Or if I forget, remind me. But how do I deal with this, right? So even if I have all these, if I'm dealing with just 1, 2, 3, n is 1, 2, 3, I have to deal with this. This is a complex number. So here we can use this Euler identity, e to the I theta is equal to cosine theta plus I sine theta. And if I put in minus here, then e to the minus I theta is going to be cosine minus of negative theta, which is just cosine of theta. And then sine of minus theta is minus sine theta. So I get minus I sine theta. So that means that this thing right here, e to the I e n t over h bar minus, is going to be equal to cosine. Is that what I did? I got that backwards. I'm looking up here. looking at my notes. I thought I had a real, yeah, a real. Yeah, I put the real as sine. No, I did cosine. That's right. Okay. So the cosine of E n t over h bar, and then plus I sine E n t over h bar. So that means that I can write this. Psi of x and t is going to be equal to, I'm just going to plug that in. Let's write this as the square root of 2 over a sine n pi x over a times this cosine E n t over h bar plus, oh no, it's minus I times all of this, same thing, square root of 2 over a sine n pi x over a sine E n t over h bar. And so now I have a real part of the function and an imaginary part of the function. And I need to, how do we deal with the complex number is to treat these two separately. So I'm going to have a real psi and an imaginary psi. And then when I go to find psi star psi, that's just going to be real of x and t plus I of x and t and square complex conjugate. So it's going to be minus times real plus I is equal to the real part squared plus I squared. And that's the part that I want, right? And so that's fine. So I need to deal with these in two parts. So I'm going to make a function for the energy as a function of n. I'm going to make a function for the real part of psi. I'm going to call that psi r. And then I'm going to make an imaginary part psi I. And then I can use those, to square those up to, I'm going to plot both of them, but that's the way I'm going to do it. Jumping back to the computer. Okay, here we are. So let's make a function for our energy values. I'm going to put it down here because I don't really care. Def E, I'm just going to call it E, right? And I'm going to pass it a temporary value of n, and it's going to return the energy levels. It's for this square well. It's not for every square well. So we can put a def, this returns the energy level value. That's fine. And it's pretty easy, right? It's just return. I don't want to type all that stuff in all the time. So it's nt squared times pi squared times h bar squared divided by 2 times m times a squared. So that'll give me the energy level. Now I can use that to define, because it comes up in my real and imaginary parts of my wave function. So now I want to define a function that depends on, I want it to give me back I want to give it my n value, I want to give it my x value and my time value, and it gives me back a number, right? I don't really want the whole function, I just want a number, and that way I can plot it and stuff like that. So def psi r of nt, xt, and t. And I like to use t's on the end of it just so I don't confuse that with my global variables. And I'm terrible with this, and I apologize, but, you know, it's fine. It'll be fine. So psi r is going to be equal to, I can just return this. Return a times sine of nt times pi times xt divided by a times cosine of e nt, right? I need to pass that nt to the function e, and I need that in here, times, what was it, tt over h bar. And then I can return, do the same thing, def psi I. It looks very similar. Nt, xt, tt. And really the only difference is it's going to have that negative sign in there. Should it have negative sign? Let's just copy that. Yeah. Oops. and it should be a, and this should be negative. I did see, notice here, I did normalize a. Did I? Let's just fix this anyway. Okay, and then this is going to be sine. And let's just put this as square root of 2 over a, square root of 2 over a. Okay, so now I have my ways to calculate those things. Now what do I need to do? So I want to calculate all these C1, C2, C3, and so forth. I'm trying to think what order is best to do next. So let's do that. Let's calculate the C's, and let's make those C's into a list. So I need a list. I'm going to make a list of C's. So CS for C's is an empty list. I'm going to add those things into there. And how many do I want to do? Do I want to do infinity? Probably not. So let's do n max equals 5. And then I'm going to call this n equals 1. So I'm going to start with 1, and I'm going to go up to 5. And let's do while n is less than n max. And then I'm going to, before I forget, n equals n plus 1. So what I want to do here is to calculate a temporary C value and then add it to that list and then increase my value of n and then do it again. So let's do that I remember I have to do the integral from 0 to a of psi n star, which doesn't matter, times psi 0 of x and 0 dx. So to do that, to do an integral, remember I have to start with the value. I'm going to add to this value, but I need to start with the value. So that's my temporary C value is just 0. Now I'm going to go through all my list. Again, for I in range length of x minus 1, because I'm not going through them all. Same thing, I'm doing an integral. And I'm just going to do CT equals CT plus psi 0. Well, let's do it the way I had it before. I'm going to do it for it's psi n. I'd only need the real part, right? I think I only need the real part, but I'm not sure now. So psi n, no, because it's a space part. I'm just doing the space, right? I'm not doing the psi, I'm not doing the whole thing. It's just the space part. And the space part is just, did I do this? The space part, I'm going to write it out. That's right. Well, I can do it as the space part is the real part with xt equals 0. That'll be the best. So I'm going to do the real part, psi real of n, right? I'm going to pass it the n number, which is n, my x value, which is going to be xi, my t value is going to be t, 0. It's going to be 0. Times psi 0 of I, right? That was my list of initial values. They're just numbers, times dx. Is that right? Yes. Okay. So now I've calculated my nth coefficient Cn. That's Cn, which I called CT. I don't know why. Now I'm going to add that to my list of C's. CS equals CS plus CT. And that should do it. Let's print out those values of CS just to see if it actually works. Print CS. I mean, I only have 5 or 4, right? So it's not a big deal. Okay, so there's my coefficients. And you'll notice this one's 0 and this one's 0 because of the way the function is. I don't need those values, but that's fine. Okay. Now, what I want to do is to, and I can make n max as large as I want. Let's go ahead and draw the sum of these functions, right? C1 psi 1 at time t equals 0 plus C2 psi 2 at x equals 0. I'm not going to let it evolve. I'm just going to plot it and see how close it matches to this thing. That's what I want to do. So I can do that. Let's do this. I have my c's. Now we can do this. For, let's see, the best way to do this is going to be, I calculated that. Okay. So for I in range length of x, I'm going to go through, so I want to plot all my x values. I'm going to, I need to calculate the sum of all those psi's. So let's call it a temporary psi. T psi, let's call it T psi, is equal to 0. Because I need to sum up all these C1, C2, C3 times their functions. For Ni in range, the length of CS, right? So that's going to go through all my values of CS and pick them out. And I don't want to just do, I want to know what number they are so I can correspond that to the wave function that I plot. T psi is equal to T psi plus C, which is going to be CSI, Ni, right? Yeah. Times, now I have to plot the real part at t equals 0 and the imaginary part at t equals 0. Times, which the imaginary part is 0. So we're just plotting the initial one. So let's not worry about that for right now because you don't want to plot those separately. So psi r of Ni, right, no, Ni plus 1. Ni plus 1. Because Ni starts at 0 and I want to do the first term. And then my x value is going to be xi, and my time value is going to be, I can put t, I already have t equals 0. And I think that will work. And that will give me my whole function. And then let's just plot that. I'm trying to think if I even need to. I do need to normalize that. So let's make a new function. I need to just check and see if it's normalized. T psi p is an empty list. I know this is messy, but if each part's not bad, I'm going to add that. T, after I get through the whole thing, T psi p equals T psi p plus T psi. And now let's plot that. And I think I can plot it right here. F2.plot, which I haven't made yet, xi T psi, which I have is the same as T psi I. Okay. F2 is going to be a plot up here. F2 equals G curve. Color equals color.red. Okay, let's run that. And it looks tiny. Maybe it's because it's not normalized. Let's try normalizing it. You get stuck on these things. You know, this is what happens when you're doing stuff live. You're like, hey, let's just work this out together. I think it's important. You're going to have problems too, okay? And just because you have a problem doesn't mean you stop and you give up. You keep going. Now, why is it 0? Is it because it's not normalized? I don't think so. Let's just get rid of this. Let's do p total equals 0. Let's normalize it. For I in range length, we've done this so many times, minus 1. I'm going to normalize this as p total equals p total plus the integral psi star psi, but I'm going to use this t psi. So t psi I squared times dx. And then that should be it. And then I'm going to say for I in range length of x, t psi I equals t psi I divided by the square root of p total. Now I'm going to plot it. I guess I could plot it in the same loop, can I? Yeah, f2.plot xi t psi I. I know this is getting messy, but it's fine. And that didn't work at all. Undefined object. Oh, that was t psi p. P. Okay. No, still didn't work. What the heck? It didn't plot anything. Okay, let's do this. Print p tot. Let's see if that worked. Okay, that's the problem right here, because that's t psi p. That was the problem right there. Now let's try it. Nope. No errors either. Okay, let's try printing. You know, I'm almost at the step where I just bailed, just because I'm already at 36 minutes. Print p tot, and let's print the length of t psi p. Okay, so p total is 0. That's why. Why is p total 0? So p total is 0. T p c I p. See, t c p I. It is. These are all 0. CSNI times psi real x and t. Psi real, see, has, when I put in t, I get cosine, so I get a 1. So it should be fine. Let me put what I have up here. Let me just copy this part. I called it psi nu, not t psi. Cheating. Yeah, it's all this. Let's try that. I'm probably just gonna make it worse. Okay, that worked. Ha. Whew. Okay, so this is my new, 5 values of functions, right? But let's just go up here and change nmax to 3 and see what happens. So you see there, I just have something weird. It's gone. Save it. We are unable to save your work. That's a bummer. Okay, what the heck happened? Let me go ahead. This is where I have my... Okay. I'm going to jump. I'm going to jump to my backup program because, you know, if you just go completely from scratch, you're going to make yourself go crazy. So here I have a backup program. Let's go with my backup. And I'll explain what's going on. But you saw that as you increase the number of in max, it gets a better and better fit. Okay. So now what else do I have to do? And I apologize, but this is one of my longer videos. So once I do that, once I make my function, now I can model it with time because I have my functions depend on time. Psi real and psi I, where are they? Psi real's right there, psi i's right there. They depend on time. So I can plot psi real as a function of time, I can plot psi imaginary as a function of time, and I can have the square of them to get the probability, and I can normalize it. And that's what now I'm doing, right? Once I calculate all those values down here, I'm just going through time. I'm making an animated graph list. I'm calculating my psi for each time. I just need to calculate the value at that point, right? And I can use my real functions and my imaginary functions to do that, which is exactly what I do right here. And if I run this, let's see if this runs, and then I'll get out of your hair, and I'll give you both. I'll give you the fixed code. And there we go. So that blue curve, that's just the initial state. I didn't model that. But if you remember my finite difference method, this is the same kind of thing, except this one's not going to make an error because it's not the exact same starting function because I didn't go to n equals infinity, but it's an exact solution. So I don't have to worry about calculation errors. I'm just plotting things that are known. And so it works a lot better in that sense. Now, what if you don't know the wave function, the eigenfunctions? What if I don't know all those solutions, psi n? What if I don't know those? Then I have a problem. Okay, there is another way to find that. We've done it before. We did it with the shooting method, and we did it with the eigenvalue problem. And so the next thing to do is to take the same idea for a complicated potential and use matrix algebra to find the eigenvalues, and then use this to plot the solutions, and that's what we're going to do. So I made some mistakes here. I would give myself an 82 out of 100, but you can see that it does work. It's kind of a complicated program, but the idea is what's important. The idea that we can represent this complicated initial wave function as a solution, as a sum of other wave functions that we know, and then model those sums is what we want to look at, and that's what we're going to do. Woo, okay, 41 minutes. No one made it to the end here, did you? Okay, well, I made it. And here's the thing. The next time I teach quantum mechanics, you know who's going to watch this video? This guy, because I'll forget how I did it. Okay, that's it. I'll talk to you later. Hopefully have a better video next time. Python. I need like a catchphrase to end, and Python said it, but